upper confidence bound. Professor Khamaru is an assistant professor of statistics at Rutgers University. He earned his PhD from the University of California, Berkeley, working under the mentorship of Professor Martin J. Wainwright and Professor Michael I. Jordan. Prior to his doctoral studies, he completed his bachelor's and master's degrees in statistics at the Indian Statistical Institute, Kolkata. His research centers on reinforcement learning algorithm design and optimization. His recent focus on developing methods for hypothesis testing, solving problems at the inference of statistics, machine learning, and optimization. This includes contributions to theory of expectation maximization algorithm, Gaussian mixture models, model misspecification, factor analysis, and non-convex optimization. We request all audience to ask questions if there are any in the middle of the talk. And yeah, over to you, Professor.
Can everyone hear me? Okay. Thanks everyone for the kind introduction, and great to be here at IISc, and thanks for the kind invite. So the topic of today's talk is bandit A/B testing, a tale of two algorithms. So first, let's thank my wonderful collaborators. So this work started by a work by me and Jubliee, that's on the left, on trying to understand upper confidence bound algorithm, and we refined some of these results in a follow-up paper by me, Jubliee, and Chiang. And then we got some recent results on Thompson sampling also. That's by me and two wonderful students. One is a graduate student at Rutgers, and the other one is at i.i.d, Kolkata. Okay, so let me start the talk with a motivating example. Suppose you are in charge of helping Syrian refugees find work, and you are allowed to use 3 interventions. You can give them either cash rewards, you can either give them skill training, or you can either give them motivational support. Okay, you want to know which intervention works better in terms of helping them find work. Okay, what is one option? One option is you allocate these 3 treatments at random. So 1/3 of the people get cash rewards, 1/3 of the people get skill training, 1/3 of the people get motivational support, and at the end of the day you do some A/B testing to decide which intervention is better. Okay, so that's for the first approach. What is another approach? So, you are in a resource constrained environment, so you don't want to allocate interventions which are not working very well. So what you can do is, you can, during the experiment itself, you want to learn which interventions are working better, and if you see cash rewards are working better during the experiment itself other than compared to the other two, you progressively allocate give more cash rewards, and the other way around. So during the experiment, what you are doing is you are optimizing your resource allocation. That leads to, naturally will lead to something we call a bandit problem. I will introduce that formally in a few slides. And of course, after the experiment, I want to still do a hypothesis testing. So there are basically 2 goals. Okay. Let me also introduce another more recent study. So nowadays, many of us wear like smartwatches, and what this study tries to do, what it will do is it will install an app on your smartwatch. It will monitor your movements, and it will try to send targeted text messages to you so that you walk more. Okay. Of course, you don't want to send too many text messages because people will just uninstall the app. You don't want to send too little notification because then people won't really walk at all. So it's not very useful. And it's also personalized. Maybe someone who wakes up early in the morning would like notifications in early in the morning, and someone who wakes up a bit late maybe would not like notifications in the early morning. Okay, So they are personalized. So during the experiment, you try to understand which person are early riser or late riser, or how much they want to walk and things like that. So you want to try to learn this during your experiment. And after the experiment, again, you want to understand whether all these interventions were meaningful at all. Did this intervention, targeted text message, at all improve people's walking habits and things like that? Okay. So there are many experiments, and in all those experiments, yeah, there are basically two competing goals. One is you want to optimize your resource allocation in some way, and at the end of the day, you want to learn something from the experiment, whether the experiment was useful or not. Okay. By the way, if you have any question during the talk, please let me know. So these kind of experiments can be naturally formulated as something called a bandit experiment, which I will define next. So what is a bandit experiment? So in a k-armed bandit experiment, also called a multi-arm bandit framework, you have k arms or k reward distribution, p1 up to pk. Each has their own mean, which I will denote by mu a. At every round, what you can do is you get to choose an arm AT, and this choice can depend on all of your previous rewards. Why? Because you try few arms and you see arm one is working much better than the other arm, so you will progressively maybe try to pull arm one much more frequently. And if you pull arm A, you observe the mean corresponding to that arm plus a random noise. Okay, so this is a multi-arm bandit problem. What is your goal? Your goal is to maximize your total reward. So yt is my reward. So this is your total reward, sum t equals to 1 to capital T yt. This is expected value. So this is the expected total reward. Or in other way, you can say I want to minimize something called regret. So that's t times mu star minus total reward. So this is the best you can hope for. Mu star is the maximum mean. So if you knew which one is the correct, the best arm, you'd pull that arm all the time. That will give you this reward. And this is what you get by using whatever strategy you use. So either you maximize your total reward or minimize this regret. Okay. All right. So throughout this talk, I will also um, talk about another bandit model, which is called a linear contextual bandit. So this will be a generalization of multi-arm bandit. So what is a linear contextual bandit? It's basically a linear model. So you have yt, which is your response, xt transpose mu. Mu is the parameter, xt is your regressor plus some noise. The difference from a traditional linear model is the following. In a traditional linear model, noise is i.i.d and xt's are also i.i.d. In linear contextual bandit problem, xt's are not i.i.d. Okay, xt again can depend on all previous observations. So you should think this is a generalization of k-arm bandit problem. Xt is kind of like your action. Okay, so whichever action gives you better reward, you try to progressively choose those kind of actions. Okay. You can see k-arm bandit is a special case. For example, if xt is one of the k basis vectors and you take mu to be mu1 up to mu k, xt transpose mu will give you this arm means. So bandit is a special case. Okay. Any questions so far? Yes. Yeah, so both the problems that I mentioned in the beginning can be formulated in this framework. So you would think that imagine the first example. So that was an example of this. So imagine the first example where you had three interventions. So you can think three interventions are three arms. Okay, and you can model the reward. So my goal is to maximize your chance of getting a job. Okay, so you can model that as a Bernoulli random variable, and you would say that okay, my probability of success for arm 1, which is cash reward, is p1, arm 2 it's p2, arm 3 is p3, and you would say that okay, I want to decide which of this intervention has better probability of success. Okay, so that's how you uh, model that as a multi-arm bandit. And the second example is a special case of this, okay, contextual bandit problem. All right. So so this is the final setup. So this is a linear contextual bandit. XT depends on history, so the data set is not i.i.d. Throughout the talk, I will assume the context space is finite. This is not really needed, but our current result needs this. So I will just assume this for now. And so, so during your experiment, you want to maximize your reward. So sum over yt, expected value of that. So that's your first goal. And your second goal is at the end of the experiment, you want to perform a hypothesis testing question. So how would you formulate that? So this is the unknown parameter, and let's say A is a fixed vector. Let's say it's targeting the first coordinate. Then you want to create a confidence interval for A transpose mu. So these are the two goals. One is bandit experiment, which maximizes your regret, and B, you want to create confidence interval for A transpose mu. Okay. All right. So let's dive into prior works. This problem has been studied quite a lot, at least in past 10-15 years. And you can divide these approaches into three categories. One is um, uh, it uses concentration inequalities. Second uses some debiasing method. What are these debiasing methods? Because the data set is not i.i.d, it introduces some bias in your data. Okay, so these debiasing methods tries to correct for this bias, and this weighted z estimator is also some sort of bias variance trade-off corrections. I won't have too much detail into I won't have time to dig into too much detail into these methods, but one good property of these method is the following: these inference methods are algorithm independent. So it doesn't need to know what bandit algorithm you are using. Sometimes bandit algorithms are very complicated, so you don't really want to use much properties of that bandit algorithms. But there is no free lunch. Since you're not using any property of your bandit algorithm, your inference might be weak. So what I will show is, I will show some simulation for the most popular one, the concentration based method. So let's see. So in this simulation, what I'm doing is I'm running two-arm bandit experiment using an algorithm called Thompson sampling. Okay. So here what I am doing is, bandits are basically linear model as you just saw, and I'm just constructing confidence interval using least squares estimators. So we know that in the i.i.d setting, least squares estimator gives you the correct coverage, but you can see in bandit setting, it does not give you the correct coverage. So you cannot use traditional methods to do hypothesis testing. You can use concentration based method, but they are pessimistic, and that's not surprising because you're not really using any property of the bandit algorithm at all. No matter what bandit algorithm you are using, um, these methods apply. Okay, so as you can see, this is the coverage probability of concentration based method. They are definitely covering more than what you need. So this is the target coverage. So it starts from 75% to 99%, and even at 75% you get like almost 100% coverage. Okay, so they over cover, and you pay a price. It's not free, because you see this is the length of the confidence interval of this one, which is the least square. This is wrong, but the length is like almost like 6 to 7 times. Yes. So coverage basically means that you are constructing a confidence interval, and you are basically detecting. So you're basically averaging whether your true parameter lies in the coverage. So you're running this maybe 1,000 times, and you're taking the average of that. Okay, so that's basically this. So 75% confidence interval means that 75% of the time the true parameter should lie in my confidence interval, and here 95% means that 95% of the time my true parameter should lie in the interval. And you can see if you need more more coverage probability, the length of the confidence interval increase, because you need to make sure that it lies in the interval with more probability. Okay, yeah, thanks for the question. Yeah, please feel free to ask any question at any point of time. I have enough time. Okay, all right. So what we do, we try to do something different. So this is a general philosophy in statistics and machine learning that we have seen many times, is that um, uh, st- in statistics and machine learning, finding nice structure in the data is always useful, right? So usually, maybe, like, let's say you are doing sparse regression or something like that. It's a very hard problem in general, but if you have nice structure in the data, many of the things become much easier. What we find out is, in our case, it's often helpful to find nice structure in your algorithm, not in your data, but in your algorithm. So we try to find out a class of bandit algorithms which gives you much better inference. Okay, so this work has its motivation from one of my favorite papers by Lai and Wei. It's a very nice paper from Annals of Statistics in 1982. So they also wanted to understand a linear contextual bandit model. So as you see, yn is beta transpose x plus some noise, and this beta can depend on everything on the past. So as you can see, where is it? Yeah, so beta can sorry, xn can depend on everything on the past. So it seems exact same contextual, linear contextual bandit assumption. Since this is a linear model, it's not i.i.d, but they still wanted to understand what is the performance of a least squares estimator. And they show is that even though the data is not i.i.d, least squares estimator is still asymptotically normal if you satisfy certain property. So beta n is the least squares estimator, beta is the true value. This is your sample covariance matrix. So sample covariance matrix per half, beta n minus beta is asymptotically normal. Okay, so this is true if your sample covariance matrix stabilize around a fixed matrix. So Bn is a fixed matrix, and this is a random matrix. This is random because you are basically choosing your x's based on your history, and it depends on how you're making those choices. Okay, so this is determined by your bandit algorithm, and it says that if your sample covariance matrix stabilize around deterministic matrix, then you get asymptotic normality. So what is the consequence? The consequence is that if for a bandit algorithm that stability condition was satisfied, you would get the correct coverage, but the length of the confidence interval will be much smaller. Okay, so this confidence interval would work. So this is a bandit algorithm which does not satisfy that property. Okay, all right. So any questions so far on the stability assumption? Yes.
How many samples? So when you do this normal approximation, what is the number of samples you're using to report the coverage?
Here.
Because yeah,
Here.
because normal approximation is asymptotic, right?
Yes. So we'll, towards the end, we'll also give you a rate of convergence, at what rate they converge. So for example, for upper confidence bound, which we'll discuss in a bit, you can quantify at what rate it converges to a normal distribution.
The concentration bounds will always be conservative compared to the normal approximation because they are finite samples.
Yes. Yeah. Exactly. Yeah. All right. Okay, so why this result is interesting, this I want to you to appreciate why this result is very powerful, because it basically tells you that even if you have non-i.i.d data, which is from a bandit experiment, asymptotically it behaves like an i.i.d data, and you can use most of the tools that are available for i.i.d data in that case. So all we have to understand is like what bandit algorithm satisfies this Lai-Wei stability condition. Okay, so this is why it's very powerful. So so what I will do next is I will just reframe Lai's stability result, which is this theorem, this one, specifically for bandit. So I'm doing nothing fancy. So according to Lai, a bandit algorithm A is called stable if there exist non-random constants NAT A star such that NAT divided by NAT star converges to 1. So what is NAT? NAT is the number of times you pull every arm in T rounds. So there are K arms. So NAT is the number of times you pull an arm in T rounds. It says that it concentrates around a fixed number. So this is a random variable. It depends on your algorithm. And it converges around a fixed number. So that's basically Lai's stability condition. And a consequence of that is you get the standard asymptotic normality. The mean, the sample mean is asymptotically normal with the correct variance, and this is the any consistent estimator of sigma square. For example, you can just take sample variance that is consistent. Okay. So you can like forget about the fact that the data was not i.i.d, and you can just use sample mean because that's asymptotically normal. Okay. All right, and you get like a confidence interval like this. Okay, and this will give you the correct coverage. Okay. All right. So all we need to understand is are there bandit algorithms which are stable? This condition is only useful if popular bandit algorithms are stable. So first what we try to do is we'll in the talk we'll discuss two algorithms. One is Thompson sampling and the other one is upper confidence bound. These are the two of the most popular algorithms in multi-arm bandit literature. So what is Thompson sampling? Is very simple. At every round what you do is you draw samples from the prior distribution. So theta 80 you construct an estimate for mean, which is your sample mean, okay, and your variance is 1 by NAT. So that you draw a sample from this prior distribution and you pick the arm which has the maximum value of this sample. So that's basically Thompson sampling. Very simple. It has a Bayesian intuition. So let's just see what happens in this case. So what I'm doing is I'm plotting. So if remember Lai's condition tells you that the number of times arm 1 is pulled should stabilize around a number of times arm 2 is pulled should stabilize around a number. The in my simulation both the arm means are equal, so you'd hope that it would stabilize around t by 2 because both the arms are same. So let's just see what happens. Yes. No, but it will have very bad regret. That's the problem. So I want to make sure my regret is not bad, but still want to preserve this stability property. Okay, so that's I want to do both. Okay, so here what I'm doing is I'm plotting n1 t by t over number of iterations, and let's just see what happens. And as you can see, as the number of rounds increase, it don't stabilize. It's almost like a uniform distribution, and this is actually true. There is a very nice paper by Calvit and Zivi. They actually formally prove this for special cases of Bernoulli bandit. They show that n1 t by t, instead of converging to half, which you would expect because both arms are equal, it converges to a uniform distribution. So Thompson sampling is not stable. Okay, so let's move on to our next algorithm, which is called upper confidence bound. So what is upper confidence bound? So at every round and for every arm, you construct something called upper confidence bound, which is just sample mean plus this is called a bonus term. Bonus term is square root 2 log t divided by NAT. And you pick the arm which has the maximum value of the upper confidence bound. Okay, and you just repeat this process. Okay, again I plot the behavior of n1 t by t. Both arms are equal, so it should concentrate around half. Let's just see what happens. So as you can see, as the number of iteration increase, it gets more and more concentrated around half. So n1t by t, so this is half, it concentrates around half. Okay, all right. So this is the main result of our paper. We formally show that for the upper confidence bound algorithm, for a k-arm bandit case, the arms stabilize. So NAT, remember I want to show that NAT divided by a quantity which is not random goes to 1 in probability. That was Lai stability condition, and turns out that for a k-arm bandit problem, this is the quantity. Okay, so 1 by square root n star. N star is the number of times you pull uh, the optimal arm. Okay, there can be multiple optimal arms. Delta A, what is delta A square? Delta A is mu star minus mu A. Mu star is the maximum value of mu, so this is positive. So 1 by square root n star delta A square divided by 2 log t whole power minus 2. And how many times the optimal arm is sampled, that you can obtain by solving this equation. And this equation always has a unique solution for any values of delta A. Okay, so we show that NAT stabilize around this fixed number. You see, it does not depend on, it's not random at all. It's because it depends on only t, delta A, which are fixed, and n star, which is a fixed solution of this equation. Okay, and a simple consequence of Lai's result is that sample means are asymptotically normal. So you can use this to construct confidence intervals. Okay, any questions on this slide? No, it works with any delta, any scaling of delta. You can you can even take delta to be 1 by root t or log t by root t. All, like, it does not. You will see why we could prove this. There's a very simple pictorial proof which I will show later on. For any values of delta, you can even let the number of arms grow with t. So k can grow maybe like square root t. So as long as k by t goes to 0, the result still works. Yes. Uh-huh. Uh-huh. Yes. Yes, yes. No, because unconditionally you get i.i.d sample, but unconditionally they are dependent, right? So that breaks the asymptotic normality. So remember, in the i.i.d linear model, what do we assume? So in the i.i.d linear model, we assume something like you assume epsilon I xi are i.i.d from some fixed distribution, right? So you see, epsilon i's are i.i.d, but this is not, like, marginally they are not i.i.d anymore. So that's why this assumption is not satisfied in bandit. So that's why you don't get asymptotic normality. Conditionally you get independent observation, but unconditionally they are not. Okay, so that's the difference. All right. So yeah, so as you can see, you get correct coverage. So this is the target coverage. This is what you observe, and it's within plus minus sigma by root n band, and you get asymptotic normality. Okay? Some simulations. All right. So it turns out that although our main target was to prove stability, which characterizes NAT divided by, which shows NAT divided by NAT star converges to 1, we actually can prove something stronger. You can show that this convergence is in L1. So expected value of NAT divided by this quantity minus 1. So this is the convergence in L1. So this converges to 0. And why this is useful? This is useful because from here you can say that expected value of NAT is exactly this quantity asymptotically. Okay. Why that's useful? Because a classical regret decomposition is the following. So regret can be decomposed as A equals to 1 to k delta A times expected value of NAT. So if you don't know this decomposition, just keep this in mind, that regret can be decomposed as this. Okay, so in order to characterize regret, it is sufficient to just characterize how many times you pull every arm on expectation. And now I know expected value of NAT is exactly this, so I can just substitute that here, and that gives you an exact value of regret. So you can just formally prove this. So regret divided by this quantity, so you just get this by substituting expected value of NAT by its limiting quantity -1. This is the rate at which it converges is log t by square root log t by log t. This is a high probability bound. And you can, as I was mentioning, this result does not depend on the how you choose your delta A's or how you choose your K. So you can basically choose various scalings of delta A, and you know exactly how your regret behaves. So for example, if you choose some scaling of delta A, that gives you the worst case regret is KT log T, meaning the lower bound is square root KT, and here you get KT log T, meaning that UCB is not minimax optimal. So you can choose whatever delta A's you want, you get the exact value of regret. Okay, all right. And it also has some consequence in, like, if you're familiar with Lai Robin lower bounds, it also has some consequence in that regime. Yes.
Told that the worst case regret of UCV is log t, root log t far from the lower bound.
Yes.
So is there any other form that any stable bandit algorithm must have this?
Very good question. Actually, we have a paper coming out that's not on archive yet. We study a class of bandit algorithms, and none of them which are minimax optimal, and none of them are stable. So yeah, so it's a natural question whether you can match both. We don't know the answer. Yeah, very good question. All right. So that's your regret guarantees. And when the number of contexts are finite, you can just apply this, because you can discretize the space. You can apply the same idea in contextual bandit too, and you can show that least squares is asymptotically normal. Okay, and you can and you can also get a rate of convergence of how fast these two converge to each other. I have some slides at the very end. I will discuss it at the end. Okay, so for UCB, for multi-arm bandit, and for contextual bandit, when the number of contexts is finite, you get asymptotic normality, you get stability. Okay, yes.
It's not finite.
Mhm.
It's a compact subset of countries.
No, we don't know how to prove it.
So like an epsilon net argument does not.
No, because the reason it breaks down is when you do this epsilon net argument, the number of arms are very, very large. Okay, and because the way we argue is that each bucket needs to have enough number of samples so that you can argue that first of all, the number of samples in each bucket has to go to infinity, otherwise this won't make sense. And it's not really clear if you can do like a epsilon net argument to do this, because the number of buckets grow with your epsilon net, right? And each bucket has progressively less number of samples. So that's why discretization argument that we tried did not work. Yeah, I'm happy to discuss more if you have some other ideas. But yeah, that's the main reason it didn't work. All right. So let's try to understand how did we actually prove this. I think the proof idea is like very simple, so that I can like explain it in a talk, and it follows from a picture. So on the left, what I'm plotting is so this is a 2-arm bandit problem. Arm 1 has mean 1, arm 2 has mean 0. I'm plotting on the left is number of arm pulls up to t. On the x-axis, it's number of rounds. Okay. Um, so here traditionally how people analyze the number of arm pools is they try to get a correct, like a very tight upper and lower bound for this, very tight upper and lower bound for this, and then they try to prove stability. And some of the earlier work, for example, Calvit and ZV, they do it for 2-arm bandit problem. That's how they analyzed the stability of UCB. But when you go from 2-arm to 3-arm or more, the it's very hard to generalize that concept. And even for 2-arm, they could only do it for like very special cases of deltas. Okay, so initially we tried this approach and did not was not very fruitful. But then we found out an interesting property of the upper confidence bound. So if you recall, upper confidence bound is kind of like a min-max algorithm. So you have like an upper confidence bound for every arm, and then you try to minimize the maximum upper confidence bound. So it like kind of like upper confidence bound trying to like squash all the upper confidence bounds at the same limit. And this is what you observe in the plot. See, what I'm plotting is, so you see arm 1 behavior, arm 2 behavior, number of arm pools are very, very different. This is like grows with t, this is maybe like log t. Okay, so even in this case, the upper confidence bound of arm 1 and upper confidence bound of arm 2 behave the exact same way. So all, no matter what is the value of mean, all upper confidence bound limits will converge to the same quantity. Okay, so that's the first observation we have. And now that you have that observation, the proof is almost done. So the observation from here is UCB for all arm has the same limit. Okay, so let's just expand it further. So here I just wrote down the equation UCB of 1 is approximately equals to UCB of k. So these are the upper confidence bound, remember, sample mean plus square root 2 log t divided by n1 t, sample mean 2 log t divided by n2 t up to sample mean 2 log t divided by nkt. So you can see there are k minus 1 equations here. So because there are k arms, so 2 of them has 1 equation. So there are k minus 1 equation. And there is another equation hidden, that's sum of the arms is t, because you get t arms, right? And I want to understand NAT, number of arm pools, because stability needs that NAT divided by NAT basically concentrates around some fixed number. So here already you are almost pretty close to the proof, because here most of the things are known. I want to understand these k quantities. I already have k equations. The only thing is these things are random, mu1 bar, mu2 bar, mu k bar. Okay, and what we do is I want to remove this randomness. Okay, so what we do is we use law of iterated logarithm. I know that sample mean minus population mean, the deviation is log t divided by number of arm pools. So you get this. So mu1, so you can write down this mu1 bar as mu1 plus minus this quantity. Similarly, mu k bar as mu k plus minus this quantity. Now you see, since UCB has a bonus term which dominates this log t, this term can be absorbed in log t. Okay, and from here you can also see log t is not special. You take any UCB type algorithm which has bonus term which dominates log t, same proof works. Okay, so that's what you do. You just absorb the law of iterated logarithm term into this term, and you get back this mu1 plus square root 2 log t by n1 t equals to mu2 plus square root 2 log t by n2 t, and you have sum of the all arms is t. Now you have k variable and k equation. If you just solve them, you get back in NAT star is this. So that's basically the proof. So it's simple. Intuitively it's very simple. There are like some technical details which I don't want to mention, but yeah, it's because of this this property that UCB of all arms has same limit. So we basically utilize that property, and now you see that why we can scale with k, scale like allow any choice of delta is because this does not depend on anything. All right. So let's move on to our second algorithm, which was Thompson sampling. So okay, yes, okay. So Thompson sampling, as we saw in the simulation, was not stable, and it's actually proved in some cases that it's not stable. Our natural question is, can we stabilize it? So let's just recall what was Thompson sampling. So this is the coverage that you get for Thompson sampling in Gaussian bandit case. So Thompson sampling theta at is the sample mean. It's drawn from normal distribution with sample mean, and this is the variance. And you pick the arm which has this maximum value of sample mean. Okay. So what I can do is I can rewrite this. So I can write theta at star as this plus zt divided by 1 plus square root n at. You can see that this distribution and this distribution is exactly the same. Zt is Gaussian. And then I pick at equals to the maximum value of the sample mean. Now you see that this looks almost like a upper confidence bound algorithm. The only difference is the bonus term is random. Bonus term is zt. Now zt is like a Gaussian random variable, so this is an order 1 term. And if we remember the proof of upper confidence bound, I need something to dominate the term from law of iterated logarithm. So this won't work, but what might work is the following. So I multiply this by a term which dominates the law of iterated logarithm scaling. So this should dominate the deviation from sample mean. So we try to analyze exactly this. We try to see if this version of Thompson sampling is stable or not. So you can write down it in the traditional Thompson sampling language. What you're basically doing is you are doing usual Thompson sampling. The sample mean does not change, but you're inflating the sample variance. Okay, so it's multiplied by gamma t. So you can prove that at least for k equals to 1, this is what we could prove. K equals to 2, Thompson sampling is stable. We also need some other technical condition, but I think this is like some drawback of our proof. We don't have a very good general proof. This proof is pretty tedious, so we don't have a nice proof. So happy to hear others' opinion. So this modification is motivated from the upper confidence bound proof works. In simulation, it works for all arms. In proof, it works for 2 arms. So yeah, so that's basically about Thompson sampling. So so let me just summarize everything. So we discussed a notion of stability, and the main benefit of stability was that in bandits you have data from like a non-i.i.d setup. So most of the traditional testing framework does not work in that case. But if you have stability, then i.i.d data at least asymptotically behaves, sorry, non-i.i.d data that comes from bandit at least asymptotically behaves like an i.i.d data. So you can use traditional methods like, you know, least squares estimator or even z estimators will work actually. Thompson sampling was not stable, but we can stabilize it in some cases, and UCB is stable, and we also find a new proof technique which also is useful if you just want to, even if you don't care about stability, you can use our proof technique to understand the exact value of regret. Yeah.
What is the price we pay we get for the stabilization of the function?
It's inflated by gamma t. Yeah, so gamma t is like little more than square root log t. So you get like pay logarithmic factor. Yeah. So if you want to read more, so this is the first paper that you wrote, which proves the stability of the upper confidence bound algorithm. Then later on, I improved upon this with stability under much more general condition and regret guarantees and some results on contextual bandit. And this is a more recent paper is on Thompson sampling, which gets stability by variance inflation. Okay, And with that, thanks everyone. Okay, so let me just go back to Subhada's question about rate of convergence. Okay, so you can show that the rate of convergence, so what is ZT? ZT is this, the standardized sample mean. So you can get like a Bayesian kind of bound. You can show that probability Z belongs to like a set minus the normal. I want to show that this goes to 0. The rate of convergence is log t by log t whole power 1/6. I think 1/6 should be improvable by maybe 1 to like a half or 1/3, something like that. But one interesting fact is even for optimal arms, it's 1 by log t. So for suboptimal arm, this is what you would expect, because suboptimal arms are pulled log t number of times. So you would expect something like 1 by log t scaling. That's not surprising. But even for optimal arms, you see like a log t scaling. So that's something interesting. Yeah. So if you trace the proof, UCB, for UCB, I think you cannot get 1 by root t. Yeah. So at least from what we understood from our proof techniques. Yeah, and you can also get like a similar rate of convergence in the contextual bandit case too, like a Bayesian kind of thing. Okay, with that, thanks everyone for the very nice questions and the warm welcome that I got at ISC. I made a lot of new friends. Went to some very nice hikes in ISC, which I never been to. I really enjoyed the last 2 days. And thanks again, and thanks for listening.
Thank you very much, Professor, for giving an interesting talk. If there are still more questions, audience, please feel free to ask.
Yeah. If you have any more questions, yeah. Yes.
So in the rate, for the regret that you showed, UCB is regret upon whatever the factor you had -1 going to 0. So you also showed the rate for that.
Yes. So that is yeah. This.
So is somehow LIL related to this as well?
Yeah. So this comes from LIL. So log t. That's from law of iterative logarithm.
So why do we expect a LIL here?
Because basically, it most of the rates in this area would look like LIL scaling divided by your bonus term.
Bonus term. Okay.
So this square root log t is directly from bonus term. You change this square root log t to something else, this will appear here. And this is exactly from LIL.
If we have just 2 arms, then regret is just like one. There is no summation. It's just one. So it's closer to sum of i.i.d. It's not i.i.d, but it's like summation of.
Sure.
So average of i.i.d. I see. Okay.
Yeah. So basically, you have to pay for the LIL because you're going from sample mean to population mean, and you get log t because the for suboptimal arms you only have log t many samples. So when you are computing regret, which combines everything, I think you cannot beat log t. So that's kind of my intuition. Yeah.
Thanks.
Thank you.
Any more questions? Okay. Thank you once again, Professor. And thank you all audience for joining us. And we also have refreshments at the coffee hut. Please feel free to have them while connecting with the professor. Thank you all and have a nice day.